I'd like to welcome you all. We've got a good mix of attendees from BT and Innovation Martlesham members, some universities and the agricultural community. So welcome to everybody. Just a few things to note, please. Can you make sure that you're on mute and that your cameras are off? It just saves a little bit of bandwidth for us. Along the screen, you can actually use a raise your hand option. So if you'd like to ask a question in the Q&A, that's the place to put them, and we'll pick them up for Fumiya to answer those questions. Feel free to use the chat function as well. You can post comments and questions there too. As I said, the event's being recorded. So Dr. Fumiya is from the Department of Engineering at the University of Cambridge, and he's also the director of Bio-Inspired Robotics Lab. He studied at various universities, including Tokyo University of Science, the University of Zurich, and the Computer Science and AI Lab, otherwise known as CSAIL at MIT, where we also have good relationships there with our colleague Steve Whitaker. So Fumiya's interests are biologically inspired robots, embedded AI, biomechanics, and the embodied intelligence. So some really interesting topics here on the agritech work. So I'd like to welcome Fumiya, and over to you.
Okay, thank you very much. Can you hear me okay?
Yes, yes, we can.
Yeah, okay, great, excellent. Well, first of all, thank you very much for invitation to this great event. It would have been nicer to see you all physically, but in this period of time, I think we just have to compromise with this option. But I'm very happy to talk about our research work in University of Cambridge. And especially in the area of agri-food robotics that we have recently very excited about. So let me start with a very big landscape about where we actually stand in the context of robotics research and development. So we're actually starting in a very interesting time in the history of robotics and engineering in general, that we're experiencing currently the rise of robots, robotic revolution. So this is the cover page of the journal Economist a while ago. They're actually explaining why we are seeing robotic revolution at the moment. So the reason is basically cheaper, easier, faster. I just want to go through a little bit one by one. So the cheaper means that we have technology costs really reduced in the last decades. Just to give some examples like this, you can find similar figures in many different places, but this is example of robotic arm cost is decreasing about 60–70% in the last 20–30 years. But this the trend is continuing over the next 10–20 years. So the price of robotic arm used to be hundreds of thousands US dollar or pounds, but now we can buy it about 20–30,000, and in the future it's going to be cheaper. And that will obviously change the landscape of technologies where they can be applied. And also the easier part of technologies that technologies are now available in markets. So if you have a bit of money and then you can actually buy them instead of building everything from scratch in your company or in the lab. So that speed up the development quite a lot. But the even more important is probably the connected and shared technologies. A lot of programs, a lot of software are already in the internet and ready for download. And even for the design of mechanical systems and so on are also up in the internet that you can download them and 3D print if you have a little bit knowledge of engineering. So this is a really exciting point in time in history, in the sense that the robotics is going everywhere, and it's even if you're not doing robotics now, it's not too late to start it because it's getting easier, cheaper, and faster. So this is a really interesting period, interesting point in history. And we just want to give you some ideas where the robots are. We don't see robots in our house yet. But the robots are actually integrated in many different places in our society. So the case in point is the car manufacturing factories that there are a lot more robots than the humans nowadays in the latest manufacturing processes. And if you go to the warehouses, that's also the revolution is happening. That instead of humans walking around in the warehouse, nowadays the robots are moving around, putting delivering items to the humans so that the delivery can be faster and more accurate. And the robots are coming closer to our lives. We all know that autonomous driving are coming to our daily life in the near future. And the delivery systems have attracted a lot of attention, especially in the current problem with social distancing and so on. So you see lots of robots here and there, and there are lots of reports available in the world. And this is one of the multi-annual road mapping efforts done by EU project. Basically, all this road mapping efforts predicts that the robots can go almost any directions related to our daily life and daily business. Starting from manufacturing, cleaning, medical assistance, but all the way down to autonomous car construction, agriculture, and health, elderly care, and the personal service robot. So this is a really exciting time that the robot can be applied to many different places. But obviously, not all of these problems are solved so far. The real important question for us, especially for researchers, is that which of these problems are solved and which of them are more difficult or impossible to solve in the near future. So that's a really difficult and important question. There's no agreed opinion about this. Expert to expert, they say different kind of things. But here is my kind of prediction from my own perspective that some of them are easy, especially the problems in the top of the list are the robots already solving lots of problems. But then as you go down to the list, the problem becomes more difficult, and some of them, like a personal service robot, it's quite difficult to achieve in the near future. So this kind of prioritization or categorization of the problems are very important, so that where we should invest as a business or where we should work on research in the university and so on. Especially for us in academic researchers, we should not try to solve the problems on the top of the list, because these are the things that are already solved or the companies are heavily investing at the moment. And our challenge is how we can go down to the bottom of the list so that we can invest for the future. And especially what I want to highlight here is that agriculture is a really interesting position in this list, because this is a not completely solved problem, but somewhere in between we solved and we will solve in the future. So that's why I want to highlight this problem in this lecture in particular. Okay. So what robots cannot do? So this is the famous video you can find in YouTube. That this is the results of the robotic competition 5 years ago in 2015 in the United States. That they actually tried honestly how robot is useful in unstructured complex challenges. So this is a competition where we replicated the disaster site of a Fukushima nuclear power plant. After the accident, and robots were not very useful that time. So they're trying to evaluate why robots cannot be used in such a complex environment. And as you see in the video, the robots quite suffer from really easy things like opening doors or closing, opening valves, and walking on the rough terrain or climbing upstairs and so on. And this is actually the reality. It's a really interesting challenge that all these complex robots trying to solve the real problem in the real world. but actually our robot have a very limited capability. So driving car is rather easy, but getting off the car is more difficult, as you can see in this video. So the interesting discussion is, I show some prior video, really interesting, a high performance robot doing complicated things, but here the rather easy things like opening door or getting off the car, our child can do quite easily, but the top researchers are struggling build for this kind of task. And why is this actually the case? And that's an interesting question to do. So to understand this, we just need to understand a bit of the state of the art robotics. So interestingly, probably 99% of robots in the world are using only two basic principles of robotics, and one of them is this kinematic-control robots. So this robot shown in this video is the so-called the kinematic-control robots that does a very fast speech motion and the precise precise placement of the body. But what they're doing is only the position control. So they can position part of the body in particular location in time. But what they cannot do is the interaction with the environment. So this robot is moving hands in a very rapid way, but they don't put too much force acting on the body and acting on the environment. So the interaction with the environment is a very, very big challenge at the moment. And the second approach in the current robotics we can use, we know, is the so-called the dynamic control robots. So because the robot cannot, kinematic control robot cannot do force control, we think about how the force can be exerted to the robot. And as soon as you put some force in the acting on the robots, we need to deal with the complex equation. You don't need to understand the equation shown in this in the slide, but I'm just telling you that as soon as you put force in the equation, it becomes everything so complicated, and we can do only very simple problems like this robot. So this robot has only two links. Exploiting force, like in gravitational force and the mechanical dynamics to swing up the of the end effector to the top. But this is probably the most complex things we can do at the moment, even with the state of the art, the technologies. So this is a really in a constrained situation. The robot can do very complex things as long as you don't interact with the environment. But as soon as you interact with the environment, you cannot really do a complex thing. So that's where we face at the moment. If you go to the real world, so this is one of the collaboration project with the farmers at the moment. So this is the harvesting side of the robot, harvesting side of the lettuces. And here robots cannot really be applied very easily because what humans doing here is very complex interaction. If you think about it, the humans are interacting with lettuce and cutting it and removing leaves and put it in the plastic bag so that they can put it in the sorting mechanism. Of course, a lot of things are already mechanized. So after harvesting, the machine in the back is doing all sort of automated delivering process of the products. But difficult bits like interacting with the crops and the fields are all done by humans at the moment. There are many challenges like this, and especially in the food supply chain at the moment. I can show you some more examples, and here is the example of how the trimming of leaves can be done. The interesting thing is that in every lettuce is different, every leaf is different, and this is very difficult challenge for modeling it, but humans can do it in a fraction of seconds to do all this trimming very instantly. Also, some other challenges that, like here we show some examples in the beetroot cooking factory. So this is a factory all located in Cambridgeshire that the cooked beetroot was manually inspected and trimmed by human laborers. And bottom videos are showing a flower bouquet factory. So this is the factory where they need to make a bouquet out of cut flowers, but a lot of things are manually handled because every flower is different, and aesthetic is very important. So we still have to rely on human laborers here. Some more example here are the quality control the quality control process in logistic company that they're checking every oranges or melons or pineapples basically manually handled so that they can measure the sugar level or the quality in general of the products they have. And the last video showing on the right-hand side is it's probably the most difficult one, which is the leek trimming process that hundreds of humans actually trimming the leeks so that they can sell in the supermarket. So we see hundreds and hundreds of workers of this kind still in UK, and all of this is actually in the Cambridgeshire alone. So we already see hundreds of people working on this kind of rather unhealthy and tedious challenges. And we're trying to do a bit of contribution to solve some of the problems over there. But obviously, the robots have very little to do in this environment at the moment. And the problems are mainly on these 5 points. So first of all, the cost issue. Our technology is very expensive. Most of the human workers are working in minimum wage in UK standards, and which is about £8.50 per hour. And our technology cannot go down as low as this one. But apart from economics, I think that technologically there are lots of challenges. Like robots are not as dexterous as humans. They cannot do complicated process, and they cannot do complex sensing problems. And the physical contact is very limited at the moment. Also, adaptability is a challenge, like how the robots can do many different kind of things like as humans do. So this is the kind of challenges we are trying to solve in the university at the moment. And one of the real challenge is that we actually need quite some paradigm shift in the technology that we have. So most of the technology we see in the agricultural field is what we call the Robotics 1.0. So these are the machines that are designed for specific tasks, optimized for one single task, and they can be very fast and efficient and cheap. But what they can do is only one thing, and that's the problem of where the robot cannot go at the moment. And on the other hand, if you go to car factories and other places where we see robots, these robots, we call this robot 2.0. So they have a lot of sensors, lots of computation, a lot of AIs. And those robots can do lots of different kind of things. So they're not optimized for one single task, but they can do different kind of things. And they have a lot of redundancy. They can be sometimes adaptive, and they can adapt different kind of things. But the real challenge here is actually they are very, very expensive. So this technology can be applied to rather high margin business like automobile industry or some other construction sites, but not in agriculture because they have a very limited profit margin. So the real paradigm we need from here on is we need adaptive robots like Robotics 2.0, but we need to make it a lot cheaper, and that's not easy problem because the cost comes with all the cost of sensors and actuators and so on. So we just need to really rethink about how to make a robot differently so that we can apply to agri-food sector. So what does it mean by another paradigm shift we need? I just want to show you one example that illustrates really nicely about this kind of paradigm shift. So this is a kind of a technology we call the soft robotics, a universal gripper. The universal gripper is actually the end effector of a robotic arm, but the end effector doesn't have an actuator, so it doesn't have any sensors. but that has actually balloon filled with the ground coffee. And the balloon has, elasticity, so it can adapt to different kind of shapes on the floor. So this balloon is adapted to different shapes of the object on the floor. But as soon as it has the physical contact with the object, the vacuum is applied to the balloon so that it can deflate the balloon and put pressure onto the obstacle of the object so that it can grip many different kind of things without sensing, without the complicated actuation or control. So this is a really interesting example because it changes our way of thinking about how to build robots with the actuator and the sensors. So the way how it works, I can, so next slide shows how this actual system works. This is the only equation they show in our lecture today. So it's not worry too much about it. But the mechanism behind this system is that we have a gripper here. When the gripper is physically in contact with the object like this, the gripper makes some deformation as shown here because of the force acting between object and the gripper. And the deformation is very important because the deformation determines how the force between object and gripper actually occurs. So the force between object and gripper can be described by the friction force and the sucking force. And the friction force and sucking force can be calculated by geometry of the gripper deformed by object. So as soon as you know the angle of contact or area of contact, you can actually calculate the friction force and sucking force, and so on. You can estimate how heavy object this gripper can pick up with this kind of equation. But the most important thing is not the equation here. The equation is not equation is actually different object to object. If you have different object here, the equation actually changes. But this equation can be actually determined by itself. There's a self-organization process of this force acting on this object and the gripper can be determined by interaction with this, and the deformation actually plays a very important role for this self-organization to happen. So this is a very different paradigm from the conventional rigid robotics, because if you have a deformable object, you can actually have an interesting interaction without too much headache about the equation and modeling of the interaction. So this is something we didn't have it in the conventional robotics paradigm. But on the other hand, the softness is not the only thing important. The rigidity is important, because if you don't have rigidity, you cannot grasp the object. So here, the deformation and the stiffening of the gripper is happening because of this vacuum applied to this. So what's really important here is the new paradigm soft robotics. So the soft robotics is really about the changing of the stiffness of the object. So most of the conventional industry robots use the rigid regime of design. So here is the robot that we usually use in conventional robotic factory. That is the old rigid materials used. But on the other hand, if you want to apply to more adaptive situation in the soft structure like this, and they can use it for manipulating of food or harvesting and so on. But the soft alone cannot solve so many problems because the force cannot be transformed. So the real design challenge here is how we can go back and forth between soft regime and the hard regime in a flexible way. So how we can take the advantage of the good aspect of both rigid and soft regime, and that's what actually what our hand is doing, because our hand is, quite soft if we don't do anything, but we can make it really rigid if we need to. So that's something we want to understand, how we can make robots like this. So we did quite some study of biomechanics and the anatomy of our body. So in this case, our body is a soft, rigid, hybrid continuum structure. This is a very interesting aspect that our traditional robots don't have. We have a very packed sensor motor unit in our body, so that's another way we need to think about. And overall, we need to do a lot more complex control procedure that allows the use of this complex structure in our hands. So I just want to show you some of the highlights of our recent research work. So, so all these robots are quite useless at the moment, but it goes down to the real fundamental question about how we can make soft robots. So one attempt we did quite some time ago is the anthropomorphic robotic finger. So we basically copy anatomy of our hands, human hands, into the artificial fingers. So we 3D printed bones and put them together with the elastic ligament and tendons, and put some motors so that we can actuate these fingers in the human-like fashion. And the motion of these fingers is quite interesting. It's more human-like than conventional robots. But the real challenge is that as soon as you have a soft body, we need lots of motors. So in this case, we make a structure of 2.5 fingers like a human hand. And then in that case, we need actually 14 motors to control, such as soft structures. And this is really useless at the moment, but that's actually captured a really important point on how complicated to control soft structure, although there are lots of interesting aspects in soft structure. So we started investigating what are the new manufacturing techniques to cope with complex structures like our hand. So this is the attempt we try with the multi-material 3D printer. So this 3D printer that is able to print both the hard and rigid and soft materials. And here we try to make a hand skeleton with the rigid bones and the soft ligament in one go. So we can wait for 7 or 8 hours to print one hand, but everything can be automated. In one night, you can make a very complex structure like our hand. We are also interested in how we can use such a complex structure, skeleton body. So this is the example of a passive anthropomorphic hand to be controlled to grasp different kinds of things by applying wrist control. So the grasping is not about the finger motion, but also the intelligent control of wrist motion, and that can actually help complex interaction with the environment. And also the geometry is very important. So our hands are developed over millions of years of evolution. So we have a collaboration with the biologists and how we can think about the good design for robots, not just copying the nature, the design of our own hand, and so on. And we, in the first place, we don't know our 5-finger hand is already optimum or not. There are many other cases, like some cases, like human family has 6 fingers, which is discovered recently, and whether there's any room for optimization in our hand or not. So we have applying some optimization problem, like what is the mechanical properties we actually need for our hand. So this is the example of the finger optimized for piano playing. So if you play piano, the rigidity is actually quite important to articulate sound. So we want to have one axis quite rigid design, whereas the other direction we want to have a softness because we need a lot of flexibility in behavior. So if you want to think about motion like playing a complex piece with the side motion of hand, we need a complex structure in the joints in the thumb fingers so that we can do complex operations in the complex and quick operation of hand can be done by passive properties of hand. So this is a kind of an interesting ongoing research about how we can make a complex structure with a new manufacturing methods. One more thing we need to think about is a sensing problem. So the electronics is usually very rigid. If we want to implement some electronics in soft structure, a lot of challenges comes with it. So we are investigating how we can make a sensors bendable and stretchable in soft surfaces. And that's another big area of research. We are experiencing a big advancement at the moment. So I don't want to go too much into details of these technologies because this is something probably this particular audience is interested in the most. But what I want to emphasize here is that we all observing the big advances in artificial intelligence, but the real challenge is coming in the context of embodied artificial intelligence, because as you can see here in the slide, AI and the control engineering is only a small part of the whole thing, and the real challenge is actually in between the brain and the environment, and which is the interface by body dynamics and morphology of our physical human bodies. So, and this part is a lot more complex than solving a neural network deep learning algorithm, because there's so many different elements in it. But we are making a lot of progress in this area, and this is the actually place where we are observing a lot of progress to make the robot revolution happening. So this is the main message I want to place in my presentation here. And then the last part I want to talk about is really the next big challenge is agile robot prototyping to make a robot revolution happening. So what we talk about so far is a really technology here we are developing in university. But the technology is not the biggest problem if we want to make innovation happen. What's more important is the team, like how we can have a human knowledge conveyed over to the location where we need the innovation. And what's really the problem is the finding problems itself. So if we don't find the right problems, we don't know what embodiment we need to build. And if we don't know what embodiment to build, we cannot really make a revolution. So a lot of research efforts we're investing in my group is actually finding problems itself. And this is something I want to share with the audience of today's lecture today. So I just want to show you some of the examples how we did all this problem finding to make a robotic evolution happen. Some of the examples is here we show the lettuce peeling problem that I showed you earlier with the collaboration with lettuce harvesting company. So here is two of the graduate students in my group have looking at problems of the lettuce peeling, and they have really challenged that this problem is not easy to solve. So they actually work very hard in a couple of days in the lab and try to solve this problem in the brute force existing technology. So here, what this robot is doing, we use the existing robot platform with the computer vision that applies some stem detection and the leaf detection using conventional computer vision algorithm. And then we use the 3D printing technologies to modify the vacuum cleaner. Actually, the vacuum cleaner is attached to this robot, and to adjust how this leaves can be picked up rather than the entire lettuce and so on. So this kind of development can be very, very quick. So the whole project was done in 3 months with the budget of £1,000. So this is actually the cheap, easy, fast development of the robot exemplified here. And even we can actually publish this kind of result in one of the most prestigious robotic journal. So this kind of development, this case study can actually instantiate how quick development of the innovative solution can be done with a minimum budget. And we have lots of other examples, similar example of this. So this is the computer vision problem with the undergrad students we have in Cambridge. So this is the fourth-year undergrad students who did the computer science education. But what she did with our collaboration with the farming, the growing company, is that they wanted to apply state-of-the-art deep learning methods to detect and quality control the lettuce before harvesting. So she went to the field to take some pictures of the field and apply this data to the existing deep learning methods. And then she managed to solve this problem in the matter of 4 or 5 months. What we did is we went to the lettuce field at the beginning, the end of the season in October, and then we had a 2 or 3 month R&D, and then we did the on-site testing when the season comes back in April. And again, we actually did the publication very quickly. Again, this is the undergrad research project, so we didn't have much, we didn't actually need it so much, the budget for this. And we can solve this problem quite easily. So the interesting thing is that deep learning method, we call this YOLO, the you look only once algorithm that's available in the internet. We can download this code from the internet, and the student can learn this with an online tutorial, how to handle this algorithm. And what she needs is just go to the field, taking the data and labeling the data, and we can get the results, like where are the lettuces, and we can also see whether lettuce are mature enough or infected, and so on and so forth. The classification can be also done very easily. So this is the kind of thing that the growers that we collaborate with didn't try in the past, and they can really see the result in the matter of months rather than years with such a collaboration project. This is a slightly more challenging problem about the harvesting problem. So here, after recognizing where the lettuces are, we need to actually pick up the lettuce by cutting it. So this one is slightly more challenging. So we did it with PhD students rather than undergrad students. But again, the rapid prototyping makes it possible to do development of such a complex rig in the matter of a year or two to make the first prototype finished with the minimum budget. So this one is slightly more expensive because we have we have the PhD student involved in this project, and the manpower is the most expensive part of the project. But we can actually do quite rapid development of this kind of project very easily. Another example we did is the tactile sensing of the mango products here. The mangoes and the avocados are typical hard shell fruits, and they are very difficult to see the maturity level without destroying them. So at the moment, everything is destroyed by sampling and to analyze the maturity. But now here we actually apply the state-of-the-art, the tactile sensing technology that we use the sensors to apply to analyze how the maturity level and the tactile sensing can be correlated to each other, and apply machine learning technique to see whether tactile sensor can detect the maturity level of mango without destroying them. So this is again a 3 months project we did with one PhD student sponsored by AHDB. Slightly different direction of research we're doing is the cooking, because the cooking is a quite interesting challenge that everyone struggle. We started with, again, undergrad students project with the kitchen appliance company to discuss what's the future of the kitchen look like. So in this particular case, we thought of the omelette making process. So we programmed the robot such that the robot can cook omelette in a reliable manner. And here, robot is actually able to make about 1 omelette in a few minutes. So we feed a lot of eggs, so the robot can try different taste of the omelette. So the robot actually make 80 or 90 omelets and give this omelet to human subject and see whether human actually see the difference of the different omelets in terms of taste and texture and appearance and so on. Again, the one of the interesting challenges is how the robot can learn to learn the preferences of individual humans. So we apply machine learning technique for to see robots can actually figure out what's the cooking process related to the human preferences of the taste of the omelette. And then we're hoping that robot can make a better and better omelets by interacting with human by tasting. A lot more thing we can do is the computer vision technique, because the cooking procedure is very complex, and the programming of robots for cooking is very, very challenging. So the new technology we're trying here is the state-of-the-art, the human pose estimate algorithm. Again, this algorithm is not developed by ourselves. We can find it in the internet. It's called Open Pose Tracking Algorithm. And the undergrad students actually try to learn to use this in a few weeks and apply it for our cooking experimental setup. So what we're doing here is that using this open pose tracking system, how robot can learn from demonstration of human cooking. So here we have a pancake. In this case, we try pancake cooking. We ask humans to cook pancake and see whether some features can be extracted from the process, and the robot actually trying to learn from humans how to cook better a pancake without really, going through the complex programming process of the cooking. So one last example we're showing here is the dishwasher loading, because with the discussion with our kitchen appliance company, the pain point of the kitchen is actually the cleaning part. So we have explored how robot can be used for cleaning of the tray. So in this particular case, we went to the college canteens to see what's the reality of the mess we see in the tray of the canteen, and we collected all this data just for using the deep learning methods. So the students, undergrad student Isabel, went to the canteen, take a lot of pictures of unstructured trays. And then we applied again the computer vision algorithm available in the internet to recognize the locations of cutlery and plates and cups, and then that's applied to the robotics so that the robot can pick and place the unstructured tray to the dishwasher. So, this is a very early prototype, of course, but we can actually try this kind of development with very short time scale with undergrad students. And all these things is possible because of the rapid prototyping technologies are available already in the internet and in our laboratory. So what I'm trying to show you here is that the real robotic revolution is happening because of the rapid prototyping. And the site visit is very important. The problem identification is the real important part of the whole process. But as soon as we find the problem we can solve, then the research and development and the publication and patents are very streamlined in the university environment. So in our department of engineering in particular, we have a very good facilitation mechanism of the industry partners, as well as finding students, finding funding to get all this, the rapid prototyping can happen very quickly and easily. And obviously, the business development is a real challenge from there. But that's something we have to address after all this, the prototyping happens in the university. So I just want to address this really interesting opportunities we have in Cambridge. So we are, all these things are not done by myself, obviously. There's so many students excited about all these real world challenges. So we have a bio-inspired robotics laboratory. We have about 10 to 15 very talented postgraduate researcher in-house. And also we have a Cambridge University Robot Society. We have about 50 or 60 really problem-hungry young undergrad students waiting for the problems to encounter. And we're trying to really find out how we can streamline this, the research development we can do quickly and the more impactful way. And another important thing is the funding agency around us. So, the company is not paying all of the research and development costs that we do. We have a mechanism of the Research Council or Royal Society or other funding mechanism trying to minimize the investment of the company side so that we can actually do the easy access to the technologies at earlier time of the development stage. So I just want to tell you all that if you know any interesting challenges you need to solve very rapidly, please let us know, and we're very happy to talk with you and see what we can do to solve your problem, because we have a lot of problems, because of Brexit, because of COVID-19 and so on. We would like to really help you innovate your business processes in the near future. So well, in summary, I just want to highlight the fact that we are actually in the middle of the robotic revolution, and we should really take advantage of this timing of the technological development. And the soft robotics is, among many other things, it's very interesting paradigm shift that we can actually make a rapid prototyping possible because of this. And then we can do the cheap development of robotics is actually possible. And we're really looking for the practical application, especially high impact application area in the agri-food sector. So this is a very, the last message I want to give you in the end. And there are lots of funding opportunities I want to show you. Maybe you can actually have this slide later that we have started this Center of Doctoral Training. We're training 50 PhD students in the coming years to address agri-food sector challenges. And if you're interested in more information, we also have the soft robotics mailing list where we can find a lot of new activities going on in this field. So soft robot, if you subscribe mailing list in softrobotics.org, you will receive the bi-monthly newsletter that we are issuing so that you can have a bit of flavor about what we are doing in the research and development. I would like to thank all the funding bodies as well as the collaborators and the students who help us doing all this exciting research at the moment. I think that's the end of my lecture today, and I'm very happy to take your questions for discussions. Thank you very much.
Thank you, Fumiya. That was really interesting. Thank you so much. There's been quite a few sort of comments on the chat, but if anyone wants to, which I'll go through in a minute, but if anyone wants to raise any questions, just raise your hand along the icon and then we'll pick you up and invite you onto the call. So Matthew Llewellyn, I don't know if you wanted to come on the call at all. You raised a few sort of comments in the chat.
Yeah, hi. Thanks for inviting me to speak. It's been a really interesting presentation. In terms of the crops, we seem to be, and as I started to talk about, where's my comment? What was I yapping on about? I think I talk about we almost seem to overcomplicate technology, don't we, and make it try and do too much. So I was talking about why are we asking our technology to reach too far now? I think we need to ask it to crawl before we walk and walk before we run. So some of those earlier robots that we were looking at were too much, weren't they? So it seems that we're taking a step back now. Are you finding it hard to find use cases for robotics? Because obviously it needs to have a strong business focus, doesn't it?
Yes, absolutely. I think that question is very to the point. That the university tend to do very high-tech, big research, because that's where the forefront of the research is. But obviously, most of the technologies are overkill for make the business happening. So I think it's very important to have how to bridge the gap between high-tech research and the actual needs in the business, and that's exactly what we're trying to do. And that's why we need to know exact problem, because that defines what technology you need.
Well, on the one with the dishwasher, I made a comment that I'll pay you £10,000 for a robot that will load and unload my dishwasher right now.
Oh, that's great. Yeah, 10,000. We can do a lot with that money.
I'll join your mailing list, and I could talk to you all day, I'm sure, but I'll leave others to talk.
Thank you.
Thanks, Matthew. We also got Henry, I think he's from Fox Robotics, about are you open for companies looking for interns for short research activities?
Yes, absolutely. So we are interested in how to strengthen the collaboration with the companies. At the moment, we do a lot of collaboration with the growers and the large manufacturer, but obviously the technological innovation happens in a smaller scale, more rapidly and more dramatically. So we're very happy to have a chat about how we can implement such internships or collaborations with the smaller companies as well.
Okay, fantastic. Thank you. Any other questions at all from anybody? Eric, did you want to come on the line?
Yes, I just wanted to know whether the slides would be available. Very interesting talk, really very interesting. I just wonder if the slides would be available later on.
Yeah. Thank you very much. Yeah, I will send it the PDF slide to Sarah, and she can probably distribute to everyone.
Yeah,
Thank you.
Okay, we've got another one come through. How does the work that you're doing overlap with the type of organisations such as Blue Prism or UiPath?
Oh, I'm sorry. I don't know about the Blue Prism and UiPath.
Okay.
Maybe.
And Andy, did you want to come on the call and enlighten us on that one?
Yeah, hiya.
Thank you.
In the technology space, there are quite a few companies that are starting to generate more momentum around sort of robotic process automation. So almost replacing a digital workforce around sort of AI and almost sort of automating the process within the technology department. And I just wondered, does that heavily, I know you've not heard of the two organisations in question, but how does that actually interlink with the work that you're doing? I mean, are you sort of looking at ways where, not just the robots, but the more sort of analytical stuff that can also replace humans as well?
Yes. Well, thank you for this comment. I think I would assume, I don't know much about this, but I assume there are lots of overlap between these two things. But I think what I wanted to highlight here is that we're trying to find out what is the good roles of the university or academic research in particular. And what we're really trying to bridge is so the university has a very bigger advantage of getting funding from the government. and also much better accessibility to young talented students. Especially in Cambridge, we have lots of genius students and who are looking for the place where they can contribute. So that's what we are really trying to do at the moment. That how we can streamline such a collaborations that not disturbing other companies or smaller companies, startup companies doing, but we rather want to cooperate with them, like with the way how we can contribute to. So with the funding support, the government funding and the student support, we are able to do very rapid and low cost research and development for the problems given. So we are hoping that this kind of activities can be bring into the innovation, and we should actually have more collaboration with the startup companies and open innovation type activities, because what university can do is also limited at the same time. So we need to have a larger collaboration framework to make the real innovation happen in the business.
Thank you.
Thank you.
We have one other question from Henry from Fox Robotics. Are you open for collaboration for grant applications?
Oh yes, absolutely.
Yeah.
Yes. Yes, we're always money hungry. So.
Okay. I don't think there's any more questions coming through. I'd like to thank everybody for joining us, and thank you very much, Fumiya. Really appreciate your time as well in presenting to such a wide audience. So thank you very much.
Thank you very much.
Okay, thanks everybody.
Thank you.
Hi, Sarah. So just to follow up, are you still there?